So, we have so far seen that the performance of idealized continuous flow immobilized enzyme reactors depends primarily on the reaction kinetics, and the basic assumption for idealized reactors was that the immobilized enzyme preparation does not experience any mass transfer or partitioning effects. So, basically we are also familiar when we were talking about the effect of immobilization on immobilized enzymes. The immobilized enzymes experience, in addition to the catalytic activity, three major external effects during immobilization. One is the conformational changes, and as a result of which the basic turnover number of the enzyme might be altered. Even the value of Michaelis-Menten constant may also be altered. The other effect is partitioning of substrate and product, which also results in alteration in the Km value of the enzyme reaction. Then the third effect was mass transfer of substrate and product, and this mass transfer, as we noticed, was at two levels, or in a very broader sense, if you consider the reaction in immobilized enzyme reaction or immobilized enzyme reactor, it will imply that in addition to the biochemical reaction, there will be four more resistances involved. One will be transport of the substrate from the bulk to the surface. From surface, the substrate has to transport to the site of the enzymatic reaction, which means the enzyme molecules that are located within the throughout the particle, immobilized enzyme particle, and then the reverse process, that means the product produced as a result of biochemical reaction has to transport back from the carrier interior to the surface, and from surface to the surface. So, therefore, the two major matrices which provide resistance to the reaction, overall reaction, is the thin film around the immobilized enzyme particle and the whole matrix itself, and the pores in which the immobilized enzyme is distributed. I think you will also recall what we had seen earlier, the diagram, that you have a thin film, stationary film around the particle, through which, and now this film thickness will depend essentially on various physical properties of the fluid, and of course, then you have enzyme distributed all over the pores in the particle, and the substrate has to transport from the surface to those materials, and similarly reverse, that is, the product has to come back from the reaction site to the surface and then to the bulk. Now, again I would like you to also keep in view or have a look at the substrate or the substrate gradient that across. Now, if you consider that this design is the thin film, then from the bulk there might be a linear substrate gradient across the thin film, and the concentration might drop at the surface, and from the surface to the interior of the particle, that means to the center of the particle, there might be again a gradient as a result of biochemical reaction, because the substrate will be consumed, and as the substrate progresses through the particle depth, the concentration will be dropping down, and it might happen, there are two possibilities. One is that you have a rather more convenient situation, that from here the substrate concentration goes like a profile like this, which of course is more favorable in the sense that around the whole particle there is some substrate available for biochemical reaction to take place. On the other hand, it can also happen that the substrate concentration drops to 0 earlier than the substrate has reached to the middle point, and therefore, this portion which is highlighted here is deprived of the substrate, and so therefore, overall reaction rate that is observed apparently is much smaller, and therefore, now of course, there might be coupled partitioning effect as are shown in the lower figures in the gradient lower, but basically these are the three major issues: biochemical reaction, external film diffusion and internal pore diffusion that are encountered in the case of a immobilized enzyme reactor, which need to be considered while we consider the reactor performance. Although in the idealized reactor performance we have not taken into account, but in the actual reactors they need to be sort of taken care while analyzing the steady state reactor performance. Now, another point which I would like to also stress is that an important feature of the performance of immobilized enzyme reactor is that one need to identify the limiting rate, the step which has a limiting rate, the lowest reaction rate. That means, a comparison between the biochemical reaction rate and the rate of diffusion, whether it is the film diffusion or the pore diffusion. One must be able to identify by some analytical method or experimental method that which is the rate limiting step, and we must analyze or design our reactor keeping in view the rate limiting step. Now, obviously, if the rate limiting step, or in other words, let us say we consider that we have a immobilized enzyme preparation with a very high enzyme loading, that means the preparation is highly reactive, that the rate of reaction can be very high. In that case, and the rate of diffusion is slow, either because of the viscosity of the substrate or other the chemical nature of the matrix. If the rate of diffusion is slow, in that case the diffusion will become rate limiting. If the difference between the rate of diffusion and the rate of biochemical reaction are too large, then obviously the one of them will be the controlling factor, and the whole reactor design must be based on that particular step. Alternatively, if you take an immobilized enzyme preparation with a very lean loading, that means the loading is very low, and that means the catalyst is not very reactive, or alternatively the enzyme is such that its turnover number is very low and the rate of diffusion is very fast. In that case, of course, diffusion effectively will not play a key role in the reactor design, and the reactor design can be easily taken care by idealized reactor performance, that means considering the reaction kinetics in picture. Now, based on these three parameters, particularly as I mentioned earlier, the conformational changes, mass transfer effects and the partitioning effects, the kinetic parameters for an immobilized enzyme are classified into three major classes. One is, we know that intrinsic parameters which are same as that of a soluble enzyme, which means no partitioning in a soluble system, no mass transfer limitations. The sole parameter is the reaction rate, and they are called the intrinsic parameters. And essentially, if we consider the rate expression, our classical rate expression K2 E naught S upon Km plus S will apply to the situation. The second class of the kinetic parameters, which are defined as inherent parameters. Now, inherent kinetic parameters are those which are obtained as a result of conformational changes only. That means, they are dependent essentially on the method of immobilization. That means, the kind of reactants you have used during immobilization, the kind of matrix we have used during immobilization, and whatever the interaction between the matrix and the enzyme under the conditions of immobilization, whatever conformational changes have taken place, whatever kinetic parameters have been modified as a result of this interaction are considered under inherent parameters, and we define them as V dash equal to K2 dash E naught S upon K dash M plus S. Basically, we define just as a prime, the parameters are just given prime, and the inherent parameters essentially are have no role to play, or not much can be done during reactor design or reactor operation. They are the final property of the immobilized enzyme, kinetic property, and they have to be, if one can determine, even in this case, now essentially I think I must again clearly stress that the inherent parameters do not consider the diffusional effects or the partitioning effects. That means, if the system has no partitioning behavior or no diffusional behavior, limitations, of course diffusion will be there, because there is a phase difference, but if the diffusion is not the rate limiting step, or rather it is quite fast compared to the reaction rate, the inherent parameters will be useful. On the other hand, in case either the mass transfer limitations, mass transfer effects are very severe, either they can be totally rate limiting steps, that means the whole rate of reaction is controlled by the rate of diffusion. Biochemical reaction is very slow, sorry, biochemical reaction is very fast and the rate of diffusion is slow. In that case, and or if they are even comparable, let us say the rates may not be absolutely very far apart, if the two are very comparable, in that case we need to consider our apparent reaction velocity as equal to K2 dash E naught S upon Km apparent plus S. Basically, now essentially here when we say that the apparent parameters essentially are those which can be modified, which can be taken care by reactor operation. That means of course, as I mentioned some time earlier, that the effect of film diffusion, the thickness of the film can be controlled by either your increased linear flow velocity in the case of a packed bed reactor, or by increasing the agitation speed in the case of a CSTR. Similarly, on the other hand, the internal pore diffusion also can be regulated by controlling the particle size. That means, the distance to be travelled, the distance of transport of the substrate into the immobilized enzyme particle is minimized or reduced. Therefore, the substrate will be available all across the particle and thus they can be modified, and therefore, they are called essentially apparent parameters. And as a matter of fact, in all possible analysis, we must be interested in these apparent parameters, Km apparent, because that will dictate essentially if we want to consider diffusional limitations also as a part of our analysis. Now, the Km apparent essentially has been a parameter which people have tried to define the quantitatively what are the parameters which can control, which can define the Km apparent, and one of the most acceptable definition of Km apparent can be K dash m upon P f. Now, where P is essentially the partitioning coefficient, that is your concentration of the substrate in solid phase divided by concentration of substrate in the bulk phase, that is the bulk liquid. On the other hand, your F is essentially equal to tan hyperbolic gamma L upon gamma L, where gamma is a ratio of the kinetic parameters to the diffusional parameters, which is defined as half K2 dash Es upon d K dash m to the power half. Now, basically if you see here in this expression K2 dash Es, I am instead of writing S0 I am writing Es, that means the enzyme concentration in the solid phase and not the E0, because as a result of conformational changes the enzyme concentration in terms of activity can get altered, and D is the molecular diffusivity and K dash m is the inherent kinetic and the Km value of the enzyme as a result of taking into account the modification conformational changes. Now, here the unique part is, while P, the parameter P depends essentially is a fixed parameter, depends on the chemical nature of the substrate and the matrix. Once the method of immobilization is fixed, immobilized preparation is fixed, the value of P is fixed, almost it behaves almost like a constant parameter. Once the method of immobilization, the nature of matrix and the substrate are defined, the value of P will remain constant and the value of Km apparent essentially is dictated by the parameter F. And in the case of F, what we call as a Thiel function, the form of F is very significant, and this can be considered to have a very unique profile. If you consider this function F, that is your tan hyperbolic gamma L upon gamma L, the characteristic of this function is that when gamma L is less than 1, that means in this region, the approximately gamma L is equal to 1. When gamma L is less than 1, the value of F is approximately equal to 1. Gamma L less than 1, F is approximately equal to 1 in this region. On the other hand, when you go at gamma L value greater than 2, F is approximately 1 upon gamma L. So, I mean, essentially when we say F is equal to 1, essentially means that there is no effect on the kinetic parameter Km, or there is no diffusional limitation. In other words, the Km is not altered as a result of mass transfer diffusion. F is equal to 1, and as we defined earlier that your Km apparent was equal to K dash m upon P F, and P we have considered as a constant parameter as far as the immobilized enzyme preparation is concerned, and F essentially if it is equal to 1, it becomes a diffusional, I mean, and that means the diffusion does not play a controlling role here if F is equal to 1. On the other hand, when the gamma L becomes higher than 2, the value of F is 1 upon gamma L, or essentially it implies that your Km apparent will be equal to K dash m gamma L upon P, and therefore the value of Km apparent gets altered by a factor gamma L. Now let us see what
is L?
L is the characteristic dimension of the immobilized particle. Now if it is a, let us say, a thin film, it can be thickness of the film. If it is a spherical bead, it can be diameter of the bead, or any characteristic parameter. I mean, just L we have defined as. Now it could vary from the.
So here Km dash is due to the conformational changes.
Yes, only inherent kinetic constant, and which doesn't. Now if you look at now the at higher value of gamma, now under what conditions, let us say, if when we have seen that when gamma L is less than 1, F is approximately equal to 1, no diffusion control, essentially. Now let us see under what conditions, if you just consider your the definition of gamma L essentially is equal to L by 2 K2 dash Es upon d K dash m to the power half. Now this is our gamma L. Now under what condition gamma L will be less than 1 or a smaller value, essentially what we are meaning. Now there are the various conditions can be from these take various parameters. When L is small, that means it is a thin film, very thin film, or very small diameter particles. The value of Km apparent will approach to that of K dash m, and there will be no diffusion control, and of course under ideal condition L is equal to 0 for soluble enzyme. L is equal to 0. So under that condition there will be no diffusion control. Second is your D is large. If the rate of diffusion or molecular diffusivity is very high, also your gamma L will be small, and therefore also there will be no, I mean, diffusion control. Third is Es is small, which also implies that the Es is small means low enzyme loading in the matrix, that refers to low enzyme loading. That means if your immobilized enzyme preparation has a small loading, the diffusional resistances will not be very controlling. The fourth thing is that your ratio of K2 dash upon K dash m, which you will recall from the basic definition of this parameter, which is a specificity constant or a pseudo first order rate constant for the enzyme catalyzed reaction. K2 dash upon K dash m is small, which essentially refers to slow catalysis. That means your catalyst is very slow, its turnover number is very low. K2 dash essentially is the turnover number, and if the catalyst is slow, then also the diffusional limitations will be negligible. And therefore, now considering these parameters, you can notice that one can design the immobilized enzyme preparation also in such a way that diffusional limitations are not that it is always desirable, but and that is one of the reasons why we call these kinetic parameters as apparent parameters. That means they are not neither intrinsic nor inherent, but they are just apparent and they can be modified if you design your system in a way. That means if you can have a very low enzyme loading, I mean, and to the extent that the overall rate of reaction of the reaction of enzyme catalyzed reaction is smaller than the rate of diffusion, your diffusional limitations are wiped out straight away. Or if you take a smaller particle, you can get rid of or your immobilization and the diffusion.
Just explain why with low enzyme loading we have gamma L as small.
So what we are talking about, we are considering this parameter, the gamma L. If the gamma L is less than 1 or a smaller value, then your value of magnitude of f is equal to approximately 1, no diffusional limitations. Now gamma L will be small when the ES will be small, and ES essentially is the enzyme concentration in the matrix, solid phase, and which is essentially the enzyme loading.
So gamma L physically defines what? It physically tries to give us an idea as to how much is diffusion.
Yeah, gamma L physically gives you a physical interpretation of gamma L is the ratio between the biochemical parameters and the diffusional parameters. You see, if you see on the numerator you have K2 and ES, both are related to biochemical reaction. On the denominator you have D. Of course, K2 upon Km is a combined parameter for the biocatalysis, but D is a diffusional parameter. So it is essentially physically some parameter which defines the ratio between the two, and by adjusting either numerator or increasing or decreasing the numerator or the denominator, one can regulate the controlling parameter. Now if you look at higher value of gamma L, when gamma L is greater than 2, as I mentioned, f is equal to 1 upon gamma L by basic definition, and therefore f is usually less than 1 upon gamma L, it is inverse of gamma L, and therefore f is less than 1, which means the reaction is under diffusional control regime. When gamma L magnitude is greater than 2, you can safely take that the reaction is diffusionally limited, and your Km apparent is equal to, as I mentioned, K dash m into gamma L upon P, and therefore which means essentially Km apparent increases by a magnitude gamma L. Now the question comes, now what are the ways, experimental or analytical ways, by which we can experimentally determine which is the rate limiting step, whether diffusion is rate limiting or not. Now there are various approaches which can be adopted, and simply by analysis, let us say if you consider at high substrate concentration, at that means your zero order regime at high substrate concentration, when you are talking of gamma L less than 1, that means a thin slice or a smaller particles, your reaction rate of a mobilized enzyme will be proportional to enzyme loading. I mean, if you make different preparations with different enzyme loadings, the reaction rate will be proportional to the enzyme loading. That means as you increase the enzyme loading, the reaction rate will also increase. And but when you talk about at low substrate concentrations, for gamma L less than 1 and F is equal to 1, the reaction velocity for immobilized enzyme will become equal to K2 dash P into F into S into ES upon K dash M. That means essentially in the first order enzyme. In the first order enzyme, if you substitute in this parameter, your Km apparent is equal to Km dash upon Pf, you get such an expression where F is equal to 0 at gamma L less than 1, and your V immobilized will be proportional to Es into S, because this is constant, P we are considering as constant, F is 1, so the V immobilized becomes proportional to S into Es. I mean, if you consider the low substrate concentration and at small thickness of particles when gamma L is less than 1. Now, in the same case, if you go further, if you take gamma L greater than 2, your Km apparent is K dash M upon P into gamma L, and now if you substitute for V immobilized enzyme, you get K2 dash upon Km apparent into S into Es. That means again a first order kinetics, we are talking of low substrate concentration, but where gamma L is greater than 2, that means the value of F is 1 upon gamma L. Under that condition, if you substitute the various terms, you will end up that your V immobilized enzyme preparation will be proportional to Es to the power half. If you substitute here the value of F, the value of gamma here, you will get E to the power half. That means the enzyme reaction rate will not be proportional to the substrate concentration or the enzyme concentration in the particle, but will be proportional to the square root of the enzyme concentration in the particle. And that is what essentially in the case of a diffusional, in the case of a immobilized enzyme system which has no diffusional limitations, the rate of reaction is proportional to enzyme loading, and which is the usual, I mean, sort of understanding even for the soluble enzyme. I mean, up to a concentration range, the rate of reaction is proportional to the enzyme concentration. But on the other hand, when the immobilized enzyme preparation is controlled by diffusion, that relationship does not hold good, and it becomes proportional to the square root of. That means, if you make a plot between L and V is equal to half L and Es, you will get a linear fit, and that can be checked experimentally by making preparations of different enzyme loadings and measuring the enzyme reaction rate. So, that is one approach by which one can essentially monitor the or determine the concentration or the controlling parameter in the case of an immobilized enzyme reaction. On the other hand, or in other words, I mean, as your gamma L will increase from a small to large value, either in the thickness or in enzyme loading, your behavior will change. Essentially, such an experiment can be even monitored. Either you increase the thickness of the particle or you increase the enzyme loading, you can see the change in the behavior on the, that means on the relationship between the enzyme loading and the enzyme reaction rate, and that can give you an indication of the I mean, controlling parameter, which is the controlling parameter. On the other hand, another way is to look at the Lineweaver work plot. Now, in the case of a classical enzyme catalyzed system, we have a 1 upon V versus 1 upon S. Mind you, this S, when we are talking of S bulk, because we are not monitoring the concentration of the substrate inside the reactor, but inside the particle, but we are considering of 1 upon S bulk, and normally we will get such a behavior, and where your slope will be K dash m upon V dash m or K2 dash E0. But in the case of immobilized enzyme preparation, which are regulated by diffusional limitations, the curve is usually convex to the 1 upon S axis. That means essentially you go something like this, and where your the slope is Km apparent upon V dash m, and essentially as a matter of fact, by plotting your Lineweaver work plot for immobilized enzyme preparation, one can also identify the extent of diffusional limitations, because then the Km apparent drastically changes. When you know the Km apparent, partitioning is of course fixed, the value of F can be noticed, and F again can give you value of gamma L. So in that way also one can determine. In fact, one of the references which has analyzed the diffusional limitation of diffusional limitations is given by Regan and Associates in Biotech Bioengineering 16/1081/1974. In fact, one of the early references in mass transfer analysis of an immobilized glucose oxidase particles was made is given in this. The third approach of analyzing the diffusional limitation is on the basis of activation energy. Now, if you look just to illustrate my point, I think I like to make you familiar with one of the experimental data which were reported. That is this is your ln V versus 1 upon T for acetylcholine esterase immobilized in polyacrylamide gel particles, and essentially when the estimation of activation energy was made under different substrate concentration regimes and with immobilized particles, one noticed a profile something like a biphasic profile. That means the activation energy got changed, and essentially this was a limit of and if you consider another situation in which the at the low substrate concentration when gamma L is greater than 2, when diffusional control was established, the energy of activation noted was E star was or delta E star was equal to 5.7 kilocalories per mole. On the other hand, at the high substrate concentration, when gamma L was also high, one got this was a parallel profile, and one get the same kind of energy of activation energy at low temperatures. At high temperatures. At high temperatures, the similar activation energy was obtained even at high substrate concentration as in the case of low substrate concentration, because at high temperature the reaction rate was high. The reaction rate being high, the rate of reaction was in that case much higher, and the diffusion became limiting. And so essentially the activation energy behavior was almost similar as in the case of low substrate and at high gamma L, which was established parameter for diffusional limitations.
Can you please repeat?
You see, now the right hand side profile, straight line profile, refers to a thick particle where the thickness is high, gamma L is greater than 2, and at low substrate concentration. We know that under these conditions the system will be diffusional limited, and the activation energy computed in this case was 5.7 kilocalories per mole. Now when you go over to high substrate concentration, over the range of substrate, over the range of temperature, initially at high temperature range almost a similar activation energy was obtained, 5.7. That means the system behaved almost like diffusional limited, even at high substrate concentration, which it should not. At high substrate concentration, the system should not behave as a diffusional limited system, but because they at higher temperatures the reaction rate is higher, the diffusional limitation was established. On the other hand, when the temperature was reduced, the system became diffusional unlimited, and the activation energy was much higher, and the activation energy higher was obtained, about 9.4 kilocalories per mole. So basically, a change in the activation energy over a range of temperature also indicates the diffusional limitation behavior. So I mean, therefore, we have three distinct approaches to monitor by experimental methods the effect of diffusional limitation in the case of immobilized enzyme particles. One is by seeing the effect of enzyme loading on the reaction rate, that means its proportionality to the enzyme loading changes from linear to proportional to the power half. The second is the nature of the Lamb-Weber plot, which becomes convex to the 1 upon s axis to the x axis, and that which essentially means that the enzyme is more sensitive to diffusional limitations at lower substrate concentrations. At higher substrate concentration, the profile is more or less linear, but as it increases to higher substrate concentration, the slope tends to increase and the Km apparent value increases. And the third is the estimation of activation energy over a range of temperature. Now finally, I think the most important thing, although after the behavior, as I mentioned, that by the experimental reactor operations in the laboratory, many people have noticed that diffusional limitations play a key role, either by varying the agitation speed in the case of a CSTR, or by varying the linear flow velocity in the case of a PFR, the rate of reaction can be improved, and so diffusional limitations can be overcome, if any. Now the question is how to analyze a practical situation. That means, if suppose we want to know that we can how can we determine the actual value of the mass transfer coefficient, how can we determine the mass transfer? So in that case, instead of, before we go to the total mass transfer, a sort of a closed box picture of diffusion, we can break it into external film diffusion and internal pore diffusion and look them separately and check if they can be analyzed along with the chemical reaction for under steady state behavior, because even the enzyme reactors that we have looked at are to be analyzed under a steady state situation. Now if you look at immobilized enzyme reactor performance with the external film diffusion, now if I look at immobilized enzyme reactors with external film diffusion, that means the substrate may be very thick, there is a thick film of substrate around the immobilized enzyme particle, which causes a substrate gradient across the film, and therefore the concentration of the substrate at the surface of the immobilized enzyme particle is not same as in the bulk. Now an ideal situation could be to consider a non-porous particle, where all the enzyme is on the surface, and the sole diffusional limitation is as a result of transport through the thin film. Now in that case, of course, one of the empirical method to determine the Km apparent was given as Km apparent equal to K dash m plus K2 dash E naught delta upon D. So therefore, of course, purely in an empirical probably solution to describe the problem, that means the Km apparent will be dependent on the thickness of the film, logical, because bigger the thickness, their mass transfer resistance will be more, and therefore and D inversely proportional to the rate of diffusion. that is also quite obvious. Now, the problem is that experimental measurement of the film thickness is not an easy task. I mean, one cannot really, for any immobilized enzyme reactor, can measure the film thickness and then make a design computation. So, therefore, an alternative analytical method has to be chosen, and if you look at analytical method, I think the best way is to look under the steady state reactor performance. That means, let us say you have a immobilized enzyme particle which is non-porous in nature. All the enzyme is immobilized on the surface, a typical particle on which enzyme is only on the surface. There is a layer of film through which the substrate has to diffuse to reach to the enzyme active site, and essentially as a result of this there is a concentration gradient before it can reach to the, and of course for simplicity one can assume a linear gradient, and so therefore rate of mass transfer essentially here will be equal to KL AM into SB minus SS. Now, this is your SB, this is SS, that is the concentration gradient. The rate of mass transfer, rate of diffusion in such a situation, let us assume the situation that this particle is a non-porous particle is packed in a packed bed reactor and you operate it till a steady state is reached. Steady state reached means the concentration of substrate at the excitant becomes constant with time. That means fractional conversion becomes constant with time. The reactor performance is under steady state, which essentially would mean that the rate of reaction and rate of diffusion are same. Rate of mass transfer and rate of reaction are identical. So, rate of mass transfer is KLAM, that is the mass transfer coefficient. AM is area of the mass transfer. AM is the area of mass transfer essentially, which is described as area centimeter square upon centimeter cube. That means the surface area per unit volume of the particle, and KL essentially is your the mass transfer coefficient centimeter per second. So, overall your its KLAM will have a unit of per second, a typical first order rate constant, and SB minus SS is the concentration gradient across the thin film. Now, this essentially under steady state conditions must be same as rate of reaction, and that is essentially here is as this is your K2 dash E naught SS upon K dash M plus SS. Now, if you substitute the magnitude of SS from this expression and simplify, you get V naught is equal to V dash is equal to K2 dash E naught SB minus V bar upon KLAM upon K dash M plus SB minus V bar upon KLAM. The steady state rate of reaction will be given by this expression, and essentially the SS equal to SS will be equal to SB minus RM or V dash upon KLAM, and therefore 1 upon V dash will be equal to your K dash M upon K2 dash E naught into 1 upon SB minus V dash upon KLAM plus 1 upon K2 dash E naught. That gives you the 1 upon V naught. Now, if you consider the extreme conditions, that is when SB is very large, SB is very high, or we are considering zero order enzyme. Now, from this expression you can get 1 upon V dash as equal to K dash m upon K2 dash E naught into 1 upon SB. This term is negligible when SB is very high, plus 1 upon K2 dash E naught in the case of very high substrate concentration in a zero order design. On the other hand, when SB is very small, or the first order design, the V naught VOR, again if you look at this equation from here, you get VOR equal to K2 dash E naught upon, or I will just write it on this. For SB very small, your VOR is equal to K2 dash E naught upon K dash m SB minus VOR upon KLAM. Or if you simplify this, simply take all the VOR term onto the left hand side, you will get K2 dash E naught KLAM into SB upon K dash m KLAM plus K2 dash E naught. You can simplify under small conditions, or 1 upon V dash for small SB will be equal to 1 upon KLAM plus K dash m upon K2 dash E naught into 1 upon SB. Essentially, if you now look at the two different conditions of the Lange-Weaver plot, in which one in the case of SB is very high, where we are giving the Lange-Weaver plot will have the slope as K dash m upon V dash m, and on the other hand, when the substrate concentration is very low, the slope will be 1 upon KLAM plus K dash m upon V dash m. Or in other words, if you just consider the two in graphical form, you get, in other case you will get something like this, almost a typical profile as we discussed earlier, that it becomes convex to 1 upon SB 1 upon V dash. Now basically the slope of this straight line will be, that means the one at lower substrate concentration. When substrate concentration is very low, this will be 1 upon KL AM plus K dash m upon K2 dash E naught. On the other hand, the slope here will be your K dash m upon K2 dash E naught. And by knowing the two slopes, one can calculate KLAM. The difference between the two slopes essentially is the 1 upon KLAM. So one can experimentally determine the magnitude of KLAM by carrying out the reaction in a immobilized enzyme reactor, continuous reactor, and getting the steady state performance of the KLAM, and then from that K dash m, K2 E naught, and essentially once you know KLAM, you also know the substrate concentration gradient SB minus SS by the equation, first equation, where we have related the rate of mass transfer, because that is KLAM into SB minus SS. The rate of reaction and the mass transfer rate are identical under steady state situation, and therefore they can be experimentally determined, and one can then carry out take the parameter which takes into account the immobilized enzyme reactor performance incorporating the external film diffusion. Of course, in this case we have only considered the external film diffusion. On the other hand, in actual reactor will also may also involve, if it is a porous particles, the internal pore diffusion will also be. Now such an analysis is applicable only for non-porous particles, or in the case particle size is very small, where the pore diffusion limitations are to be taken as negligible. And we will continue with that in the subsequent.